Okay, welcome back everyone. In this video we're going to be looking at the different types of energies that are involved in simple harmonic motion. And so we'll just use a simple example of a block on a spring. And so as this block moves, there's going to be energy stored in the spring as potential energy. So we'll call that potential energy due to the spring. And we haven't really talked about what this is, but if you think back to work, work is basically force times distance. And we've learned recently that the spring force is related to kx. So if I graph it, it basically is a linear relationship with the slope of k. And if I want to find out the amount of work that occurs on a spring, I simply find the area of this, and so the work is the area of this force versus distance graph, and what I get is 1/2 times the force times the displacement. And then if I plug in that the force is kx, I get that the amount of work is 1/2 kx squared. So at any time, the energy that's stored in a spring is simply 1/2 kx squared. And we can also say that at any point the kinetic energy of this object is going to be 1/2 mv squared. So the total energy, or TE as we'll call it, is always going to be potential plus kinetic. And so the total energy will be equal to 1/2 kx squared plus 1/2 mv squared. And it's really interesting to see that both of the energies kind of end up having a similar form. So that's kind of cool. And so now what we can do is we can think about sort of the range of motion. So let's say that this is actually where x is equal to 0, or the so-called equilibrium. And let's say that we stretch it out a certain amount here where x is equal to a. That means that there's another place back here where x is equal to negative a, and that's going to represent the maximum for potential energy. Okay, so the potential energy max that we could get is 1/2 k a squared, because that's the furthest that you can stretch or compress the spring. And because energy is conserved, if we stretch the spring out and then let go, we're talking about starting with a kinetic energy of 0. So we could argue that the total energy of simple harmonic motion for a mass on a spring is 1/2 k a squared. And I have a neat little applet that kind of shows this. And so here's a mass on a spring, and what I can do is just hit play, and you can see a couple things happening. There's actually a lot going on this screen. So over here on this graph, you see u comma ke comma et. So u is another way of saying potential energy, and that's actually the one in red. And the kinetic energy is in green, and the total energy is in black. So let's kind of take this step by step, and let's first look at this point right here. Look at that stop. So what we have is basically the kinetic energy is 0 because the spring is compressed as much as it can go, and so the mass is stopped. The potential energy is maximum, and it's actually equal to the total energy. Then as you go forward, the potential decreases and the kinetic increases. You can think of this as the spring is causing the block to accelerate, because remember, the restoring force is going to actually point to the right at this point because the block wants to go back to the 0 point to equilibrium. Because of that, it'll accelerate to the right, and the kinetic energy is going to increase, and potential will decrease because actually the spring is less compressed. Then when we get to x equals 0, kind of right there, close enough, we can see that the kinetic energy is at a maximum, and the potential is basically 0 because x is 0. So you can see over here the velocity is at a maximum. And then at the other end of the spectrum, finally, we have the same thing as at the left side. We have where the potential energy is greatest. So there's two maxima at plus A and minus A, and two places, therefore, where the kinetic is a minimum. Okay, so now we bring this back to here, and what we can do is actually write an equation for the speed of the mass at any point. Now we know that the total energy is equal to 1/2 kA squared, but we also know the total energy is 1/2 kx squared plus 1/2 mv squared. So we can just plug in 1/2 kA squared for the total energy. That's equal to 1/2 kx squared plus 1/2 mv squared. And so what we can do is we can cancel out all the 1/2s and get the stuff with the k's on one side, and that's going to equal to mv squared. We want to divide everything by m, and then finally we want to take a square root. Okay, so take the square root of that, take the square root of that, and so what we end up is something that looks like this, that the speed as a function of position is the square root of k over m times a squared minus x squared. And so we can check this to see if it makes sense. First of all, what's the speed when the amplitude is, what's the speed when the displacement is equal to the amplitude, so the furthest it can go? Well, we plug in x is equal to a in this equation here, and we're going to get, as we would expect, that v will go to 0. And then finally, what's the speed going to be when x is equal to 0? So this is the equilibrium position. Well, this is another way of showing that the speed is going to be a times the square root of k over m, because what happens is we get the square root of k over m, a squared minus 0. So that's all gone. The a comes out of the square root, and we're left with this. Okay, now I want you to remember this because we will see this a little bit later, and this is the maximum speed that you can have in simple harmonic motion. Okay, so next time I will show you a video explaining how to calculate things with this total energy. So that's it for now.